Okay, hey everyone. So I'm going to do a talk on Monorepo Build Systems, or rather what Google does for themselves, which has some extra features. So I think for 100 companies this would be a consideration. Would you do the same? But no more than that. Everyone else would only be interested in following me here if they're curious about what Google does internally. So who am I? I'm Paul Hammond. I have a bunch of online resources for trunk-based development, including this video. It should be a persistent URL there in case I have to re-record it. I have a book on trunk-based development as well, and then also a more recent book on value stream mapping for software delivery teams, and that's interesting but unrelated to this topic. So the roadmap for today's talk. First of all, I'm going to go into DAG-based build systems, Google's Piper, their rationale, the simulation that I've made that's clonable on GitHub, talk through the various builds and test scenarios within that one, so be in IntelliJ, and then maybe the special source, which is the sparse-checkout capability. So although Google don't themselves use Git for their monorepo, and Rachel Botvin and Levenberg's monorepo paper from 2014 refers to this as subsetting and use of a checkout system called clients in the cloud. It is the same stuff. It's sparse checkout in Git, if it were Git. Then I'm going to pivot to depth first recursive build systems, which is the classic enterprise choice. It's the same repo, it's a different branch. That's a branch that, although it has some history with the main branch, it's not worth comparing the two, other than to confirm the fact that some of the sources are the same. And I talk through various build and test scenarios for that one, and then end on discussions around the pros and cons of this setup, or at least a subset of the pros and cons, because I'm pretty sure there's a lot more than I've thought about. So Google's Piper version control system and build system. Thousands of applications, many thousands. Services, components, libraries. Again, the talk from way back said that was 9 million source files in one branch, which is a trunk. And they pivoted from Perforce to Piper, their in-house thing, in order to implement horizontal scaling. So this is probably distributed worldwide, supports 25,000 plus committers, so that would be devs and QAs, with over 90 terabytes of history. Now you wouldn't clone 90 terabytes of history to one dev workstation. And even if you could, the checkout alone would kill Visual Studio, IntelliJ, whatever you would throw at it, would probably just choke and die. So the devs and QEs use a tool for smart subsetting, and this is the special source, and that seems to work well with Bazel, their choice. So I link to the paper. Google's rationale. So there's many printed and discussed rationale, but I've tried to distill it down to what I think is the strong arguments here. So they can make atomic changes across multiple projects simultaneously, maintain consistent dependencies, and very effectively share code at source code level. So if you were using Maven or NPM, you'd be sharing codes at a binary repo level. But in Google's case for the monorepo, that's a source dependency in the version control system itself. And that's across the entire engineering organization. And it's true to say they don't have everything in the monorepo. I think what would go in the monorepo is stuff that Google has the primary relationship with the end users. So that would be websites, services, all sorts of things like that. But not Android, where someone else has the relationship with the end users. That would be Samsung, the licensee, and others. So Samsung might slow down on releases that Google are doing, and Google would wish to have an evergreen continuous deployment system to everything if they could, can't for licensees like Android. So there's a different place for the development of that. So very important. And dependency management this way allows lockstep upgrades without missing space, lockstep releases. And it enables lower drama, large-scale refactoring. Turns out, a couple of days ago, there was a new publication on a LLM-assisted large-scale refactoring So I think it's a telling of the story of branchable abstraction without saying branchable abstraction, but I stand by to be corrected on that one. So here we go, first major piece, the DAG-based build system done Google style. So they have released Bazel from Blaze, but I'm going to talk about some applications that we're going to use for our simulation. Two applications, Monorepos rule and directed graph build systems are cool. So these are contrived applications, they're just a main method that spits out something to stand it out. And then inside these two applications, there are module dependencies on a bunch of, every letter of the alphabet is grouped into some construct. Vowels are here somewhere. And the letters of each of these words is picked out as a dependency. So Monorepos rule has 2 E's, there's some 4's here somewhere. What's that one? I can't tell where those lines are going anymore. But this is a GraphViz diagram, and I can zoom in Reveal.js, and we see some, as well as has going on, we see some in Java terms inheritance. So val extends val base. Val base is a module, and val base has a Rust dependency. Square rectangular blocks are Rust, and then the ovals are Java, and then a helper class. But everything that's in the class tree is mapped here. And there's some things that are not used by anything. There's some things that are partially used as a module, and there's many where you see two red and blue. You see things that are used by both applications. Anyway, so this is our contrived application, and they basically only do something by the main method and then quit. Okay. Oops, I'm not advancing right. So the simulation GitHub repository. Yeah, just a standard clonable GitHub repository with some instructions on how to set yourself up, and then a talk through of the things that you would do. So some types of learner are probably just going to pause the video here and then dive off to that repository and then kind of tune me out as they have me in the background and explore themselves. I know plenty of those people. So module dependencies within that system are declared. I have a compile, dist, and test shell scripts in various places in the module tree, and then each of them can define another dependency to another module just by having a fairly standardized section within the shell scripts. This could easily break if somebody puts a gratuitous carriage return in there, or maybe even doesn't use the right type of quotes. And this is in English, this would be tests for component vowels are depended on by the prod code. Depend on prod code for the same to compile. So you could see Java tests in here as part of the module, and then tests is missing from this module definition. So they're related, they're both vowels, but one's in a tests directory and one's in a Java directory. And then we also have libs in the same way. So we're using JUnit, testng would be a choice. I'll be berated for using JUnit 4, but it's one jar rather than a couple. Now, if you were using Git for your corporate monorepo, you probably wouldn't check in your jars, which is what's implied here. You'd use Git LFS. Anyway, let's go across to this thing and talk you through it again. So Java applications, 2 applications, directed graph build systems are cool. It's not conventional in Java to have underscores in directory names, but we're going to because it works with shell scripts. And then Monorepos rule is the second application. So there's a compile script in here, some standard lines at the top, all those dependencies we talked about, and a bunch of helper scripts. So they're in the repo. You can see them down here. and there's a lot of similarity between all the compiles. The dist is the same sort of header stuff. So we call the compile script, then we go on to make a jar, and that's it, completes it. Or maybe we echo something useful to the user. So they're all over the place. Components too. The classes of components are fairly simple. Remember, each val extends val base. The classes of the applications are a little bit more complicated, but not much more so. So we had Java and Java tests. Same directory structure within that. Tests, then another tests and dist. We also have a Rust folder. Rust has single source file. Rust has its own build system, cargo, and I've not managed to vendor in all of the bits and pieces I wanted for Rust existence here, so I'm just using cargo as is. You'll see that in the build log in a minute, and I'd prefer to have compile sh call Rust C rather than cargo, but I haven't been able to solve that. Maybe somebody can contribute that. So anyway, so there's the Rust component. There is no Rust tests, but there's lots of stuff. So let's have a look at a compile. Whoops. Right, so we're compiling monorepos rule for the first time. There's the Rust compilation. Lots of deps, they're not checked in. So Rust is maintaining its own binary cache. If I run that a second time, this build system I've contrived skips steps that have already been done. It's using timestamps, which is not particularly sophisticated. Now if I pull this back and say, I should run test 2, well, that's in a different directory. Tests.sh. Right, so it ran a single test for monorepos rule, which did the same stuff. It output to standard out. Oh, incidentally, each val in val base will put parens around the actual letter that was passed in from the subclass. But that's not all I can do. I could do test and dist. And that then does the test again, or actually it skips it, and it goes on to make a distribution. So I had in the Java application 2, the directory, I could have dist there, which doesn't do the test, and it goes on to make the same jar, and it gives us some advice on how to test it. So let's see, Control C, I'm on a Chromebook here, and there it is, it spits out the same stuff the test did. Anyways, so that's the application. There was some things I didn't show you in the directory structure. The lib folder. There it is. So we're vendoring in binaries. Hamcrest and JUnit are both used by the tests, and they're put in here without a version suffix. So that would mean that everything in Java tests that needed JUnit would depend on the same version of JUnit. And this allows for your lockstep upgrades, but it was also maybe problematic. There's some folklore from the middle 2000s where the actual upgrade of JUnit from 3.8 to 4 point something was hard and couldn't be completed easily by a summer intern. So there we have the directory structure, some shared scripts, and we can talk about the execution of some of these. So we talked about the dist, we ran that once, and we have a sequence diagram here. So this is a mermaid diagram, and it's the SVG thing just inlined in the page. And if we think of some compromise here in that we're not differentiating anymore on tests and compile, which is maybe moot for the target in the Java directory where there were no tests, but we'll come to that in a minute. Monorepos rule is our intention, that's what we've asked to do, and that's the first script that we tried to invoke. The human to the left of this invokes monorepos rules compile.sh, dist.sh. But this one in turn reaches out to fricatives, nasal, sonorants, doing the same thing. And then it gets to vowels. Vowels before it completes has to invoke the compile script of vowel base, which is Java, which in turn invokes the compile sh of the Rust stuff, which could probably be shorter, but in my case it's making a linkable object, an SO, and then that returns to vowel-based Java, which then acquires the SO from the relative directory, not from a binary repository like npm or Maven Central. Then it goes on to compile the prod code for vowel base, and then the compilation of the prod code for vowels. And then we're back to the starting point, which was the intention to make monorepos rule executable, or executable jar. So we bring in all the classes, not jars. We bring in the SO again. We're compiling Java prod code for monorepos rule, and then we're making a jar from all of that, including the SO squeezed into there. So that's the sequence diagram. So you start with the leaf, right? Monorepos rule, and it recurses backwards through the entire everything to build what it needs, but only what it needs. So the checkout could be bigger, or you could be missing a piece, like say fricatives, and then it would just bomb out there if that wasn't in there. So there's no correctness checking other than the attempt to invoke. So zoom out. Next slide. We did show that, the execution. Next slide. Tests for the same. So we changed to put tests in the directory, and we changed from compile to test, and then we ran that. And if we zoom in again, we're seeing pretty similar stuff, and we don't see any tests yet, but we do see tests down here. Right, so in the intended target, which was monorepos rule, executable jar, we're running tests for that and executing the tests. It's interesting. So there was an additional tag, an option, test depths 2. So this time, if we added that to the invocation, not only would we compile prod code for each, but we'd go off and do the tests as well for the same. So it lengthens the build. I note here that a compilation in Rustland is not ideal. And then we carry on acquiring all the class dependencies. We go through the regular pieces, which was the tests for monorepos rule, then executing those tests, then making the jar as it did before. Then there's some convenience scripts like run all tests. So regardless of what was in there, we saw a second application that would run those tests too if I'd done a git clone. I'm going to come to this later, but we have a sparse-checkout feature. It wouldn't matter what was in my checkout, this would recurse deeper in the directory structure looking for everything that was a test and run it, which could then call backwards into a compile, depended on compile steps and others. Google would use my naive technology. They would need additional features before they did. So I'm borrowing a diagram from Martin Fowler's site. So what about tests? If we weren't differentiating on tests within each test directory, we'd be in a very problematic state if we were running all tests for everything. So you'd probably demark into unit, service and UI tests, and then you might choose across the entire structure for test dependencies too. You might choose to do everything's UI tests followed by, unit tests followed by everything's service tests, and then say the Selenium or Playwright or Cypress using UI tests, functional clicking. Some call that end-to-end, previously full stack tests. So those would be slowest, most brittle perhaps, but the ones that would give you fastest intelligence on whether your pending commit was good or not would be the unit and service tests. Google called those small, medium and large. which I mentioned here, and Mike Bland has an article on that. So you could also do something more sophisticated, like all the scripts run relative as well, not necessarily from the root folder. So we could say we'll go for the unit first. In fact, there probably shouldn't be a dash on that. Then the service, and then the UI ones, but not run them for all the dependent on modules, just run them for the target module, which was monorepos rule. So I haven't coded that bit, which is why I didn't catch that bug. But you might have those features in it. So part 2, we're going to go into the sparse checkout technology that is indicative of Google's Piper reality. So we had Monorepos rule as an application, and we also had the other application, which was Directed Graph Build Systems are cool. It's not the class name, that's the module name. So we maybe need one and not the other for what we're trying to do today, and we could imagine that everything we're dealing with here isn't a single class in the module, but it's thousands or tens of thousands of classes for some really big assets like Google Maps, Google Docs, and others. And we would want to really focus on the one we're dealing with. So we'll carry on pretending we're only working on Monorepos rule. Yeah, that doesn't display very well. So we're going to do some stuff here. We need to init. This I've called a gcheckout. So let's remind ourselves of the directories in play here. Directed Graph Build Systems are cool Monorepos rule. So we're going to do, and I have no changes, so this is the right moment to choose to focus on one application. So I've done it, and I'm hoping it's going to, yeah, IntelliJ didn't particularly wake up fast there. So we've lost all the directories of Java, Java tests, and Rust, and libs. And we just have, a skinny entry-level sparse checkout plus some defaults, including the shared scripts folder. So now I'm going to do an add. So calling the same script module, gcheckout, and this time passing in the path to a module. It runs through a bunch of things recursively. Right, so we have Java and applications is back, but when I go in, there's only Monorepos rule. The second application is missing. Same with tests. There's nothing to see in the libs. It'll be identical for both. And the Rust thing was dependent on, so it's in there too. So if we wanted to bring back tests, test and dist, it runs through and works. But if we wanted to say target the missing application, it's missing, can't be addressed. So that's the nature of the sparse checkout stuff. You could maybe be working on something that was depended on by both this and the other application, and then you could modify your checkout to include the other piece too. I can't complete anymore because that's not my file system to use completion, but it would have been Directed Graph Build Systems underscore in many places are cool, and then it would add that to this checkout. And then I had a reset too, which would take us backwards. But this with Piper probably, I don't know, works in this sort of way. And whereas I'm currently using a Debian system within the Chromebook and a X4 file system, in Google's habit since 2012 is to use clients in the cloud, which is a fuse-based system. So you're using RAM and network to mount something that purports to be a file system, but it wouldn't work if you were offline. But it's perfect for Googlers because it's probably bigger than the Chromebooks they're using for devs could handle itself, and it wouldn't be slow if it's Google. So Google have additional value in the directed graph. So they've been working on this for 25 years, and it was first worked on by humans, dividing one larger module into two and then having a dependency between one and the other. But sooner or later, scripts joined in, bots, things checking overnight, things checking during code review, feedback out of cycle, things like that. And more latterly, LLMs will be weighing in, or maybe even making changes automatically, saying, I've broken that up for you. So often complaints would be, that's too big, make it with two optional child modules, or that's too small for it to be a module, or this duplicates something else and maybe you should consider dragging all of this code across to that. So they've curated this large module hierarchy across multiple languages over many, many years. And it's ultimately immensely valuable. It must be the most economic way of representing a larger system in a directed graph. It's been honed, and if the LLMs are playing now, they'll run scenarios saying, scenario 1, can I break this up into 3? Scenario 2, do I combine it with something else? And then they make some judgments about which of the two was better, and then suggest that in a pull request to a dev team, to delivery team to finalize. So it's ultimately a fluid thing that initially at least was created by hard work, cerebral analysis, trial and error, and ultimately isn't something that's so casually rebuildable to that level without all of that cumulative curated effort. So we finished on the directed graph system and the Google special source, the checkout stuff, the sparse checkout stuff. But we should really go into the other world, which is what enterprises would more classically use. So, init, reset. So we're going to check out a second branch. Some things disappeared. Java tests, Rust have disappeared. Applications and components now. I'm using Maven, which is a classic enterprise choice for Java. Turns out Maven can also do the Rust bit as well, so that's all good for us. So inside applications, we see our familiar application names. Structure is slightly different now. Java and Java tests are within there. Single class. The single test. Tests are contrived. Did I show you that? Very contrived. Everything has a POM, every module has a POM, and then interestingly for Maven, parents of modules are also modules that have a POM that themselves don't make a jar, but then this is necessary for recursion into the other two. So I have module declaration here for the two modules. It doesn't matter about the order. And then right at the outermost level, I have a naming of applications and components as child modules of where we are. So anyway, Java works here, and I could do a Maven. Let's do, hang on, let me just remove the target directory, which is a vestige from the other branch. So if I do Maven install, classic starting point for a Java Maven developer, there's lots of output, including the Rust piece, and it's making many target directories all over the place. The target directory for the other one was a single one in the root folder, much like Bazel does. Downloading stuff from Maven Central, caching that locally for my user. Not all of that's needed for the application, but it is needed for Maven. And then some timings on things. But if we run it a second time, it's a lot faster through the second time because it's not filling the Maven cache. But it is doing tests for every module it recurses through. So Maven has a thing called reactor which works out the order of things. But we can, closer to what we're saying is a best practice, there it is. We can name the application we want and say, which is PL, And then with AM, which is, maybe you can't see it, is saying all other modules that are needed for that. We can make Maven behave more like the directed graph system. And it runs through a subset, so it doesn't, in this case, build directed graphs. Build systems are cool, or any of the component libraries that neither used. And then did I do that right? Quieter Maven. Okay, I made a shell wrapper for Maven, which makes it a bit quieter. Waiting until the end to tell you all the steps that it did. This ultimately helped me build the sequence diagram. But these are the steps it went through in order. So Maven starts at root, works out a graph for everything, works out then which ones it needs to do for the intention, which was to build the goal, which was to build monorepos rules executable, and then runs through that in that order. So it is another branch. It's all there, more small differences in the README. So no more shell scripts, instead we have a sprinkling of pom.xmls. There's the quieter output. Maven's reactor picks the order, and then we want to talk through a sequence diagram. So this was us choosing that creation of monorepos rule application, but we're telling it that we want to make the executable, which is the package goal, and package depends on test. So we're going to see a different order of things now. So the most dependent on least depending thing that Maven could work out to do was the Rust module, Valbase. But we're combining here Valbase and Java and Rust into one line just for convenience. And also, whereas you might consider these separate vertical lines for test and for the prod thing, I'm combining them in two. So I did that for the other sequence diagram. So Java test compilation, run the tests, make jar after Rust compilation, Java compilation, acquisition from a local representation of Maven Central of JUnit and Hamcrest. They probably had version numbers actually. Then the next one, after doing that, the Maven reactor then calls out to vowels, then nasal, then voiceless, then fricatives, then whatever the other ones are. Then ultimately it gets to the intended target, which is monorepos rule, which goes and drags some jar dependencies, not from the local Maven Central, but from the target folder for each of these modules. And when we pulled in the dependency for Valbase, it had transitive dependencies, so they're pulled in too. Maven's, one of its features is handling the transitive dependencies for you. Then ultimately you compile, and then the compilation of the test, then the running of the test, then the making of the fat jar, the ordinary jar. There's another step which is called an uber jar, which unzips all the other jars that were made and then rezips them as one thing that we could now consider to be its own executable. That detail you don't need to delve into too much, but Maven has a lot of plugins which are XML declarations for precompiled and separately downloadable Java bits and pieces. So we're at the discussion stage. So the discussion's two dynamics: depth first recursive, the classic Maven, Gradle, mill way of doing things, versus directed acyclic graphs. The second dynamic was the sparse-checkout tooling. So we're going to very briefly go into those. So my sparse build technology doesn't have a reverse map. Google system undoubtedly does. It might these days be Kythe, although I'm not entirely sure what the ongoing development is for that, but it was been talked about for the last couple of years. But with this system you could probably say hey, what depends on me? And then, hey, can I add all of those depending things because I've just changed this? And you could be really sure in your pre-checkout, pre-check-in, pre-commits cycle that you've found all impacted sources. For Martin Fowler's site, I wrote an article on test impact analysis, which I'll try and link to. And that stuff's codified in this large DAG. But you would want to query it, not necessarily without reading it every single time. So where would you keep that? So a naive me might say, let's make a map folder in the repo and keep updating it, but you probably shouldn't do that if this gets too big. People would not thank you for that being the eternally changing file with every pull request. So it could be an external system, database of sorts with smarts. And then you might say you would need, and I haven't made, a way for a commit hook to stop you from proposing a pull request on something that is incomplete. So your fast fail script could say your sparse checkout should have this and 12 other modules because you have changed something in a TypeScript foo banana as a module. So shell scripts versus Bazel. So I only use shell scripts for one reason, which is they're teachable. You don't have to have any training on a grammar and maybe lose context as you're being introduced to that. And there's no installs for everyone that has Bash at least, which includes Windows these days. Then there's a bunch of downsides, like StyleArc is actually a fairly clever system, quite extensible, terse, elegant grammar, pseudo-declarative, with the ability for contributions, plugins, whatever, to be made in a number of languages. It doesn't just constrain you to Java for the plugin pieces for that. There's Python, TypeScript contributions too. So my thing has loads of repetition, StyleArc doesn't. And then my dependency tracking is very naive. I'm just dependency tracking to module, whereas within Bazel's use of StyleArc and dependencies, you can go all the way into a package or a class within a larger module to make that really optimal on compilation speed and then size of ultimate zip. So there are some advantages to a DAG way of doing things over depth first. Lockstep upgrades of modules and binary depths. We mentioned that right up front. Maybe it's important to say at this stage that does not mean you have to lockstep release something. So Google Maps could upgrade a common library that they have with Google Docs, and Google Maps could be releasing every 2 days, and Google Docs could be releasing every quarter. And it doesn't matter. It'll all work. It's just that if the Google Docs team decided they didn't want to upgrade a module and Google Maps did, Google Maps would win as long as they didn't break any of Google Docs' tests. So they can assert over a number of feet dragging techniques that a team might do to otherwise not keep abreast of all the upgrades. So it's worth noting that Emerson talked about a foolish consistency is the foolish hobgoblin of little minds, or some reordering of that. And it's true, you shouldn't just aim at consistency in software development and delivery because it feels nice. You could embrace a number of non-consistent things and still consider yourselves having made a fantastic long-term maintainable solution. And I'm sure there's many other claimed advantages for the depth-first build systems that could be back-ported to the likes of Maven, Gradle and others, including the sparse checkout tricks and compatibility. So let's go and have a look. We talked about this, right? You must recurse into applications and components, and then we had a look at this one. You must recurse into monorepos rule and direct graph build systems. Well, you could have optional equals true in here. That would be if Maven supported attributes at all. So it would probably be an element called optional. Never mind. They'd have to implement that. So then the disadvantages of DAG-based build systems. Some classes are going to be discovered late. If compile calls another, compile another folder calls another one, calls another one, calls another one, and something was missing in the checkout, you might find quite late in an attempt to build that something is wrong. Whereas Maven would attempt to navigate through that entire hierarchy for everything that was checked out, build a list of things, fast fail on something that was inconsistent or mentioned and absent, and prevent you from going through a protracted compile and test loop before failing. And I'm sure there's many, many other disadvantages. So that's where I'm going to pause. I might redo this presentation, fix spelling mistakes, but also if somebody does a pull request into what I'm releasing, and it's better, then I'll re-record and give credit. I'm probably not going to make this into a formal build technology that's for everyone, but if somebody else did, I would link to that. Anyway, I hope you enjoyed that. Thanks, bye.